Okay, so let's go ahead and talk about this one. So what were some of the answers that we came up with? What do you guys think?
We think it's to the right.
Okay, why?
Because, so, the y components of both are the same, so they're going to kind of cancel out. But then the positive charge emits an electric field away from itself, and the negative creates an electric charge towards itself.
Right. So if what we did here was we actually drew the situation, what we would see is something like this, right? So we have what we're given to start with, and then what we want to do is we want to draw what the electric field looks like for each one of these. Now we know for the positive charge, electric field radiates outward like this. So at the point we're interested in, this electric field, we can call it E sub plus, looks like this. And then we can do the same thing for the negative charge. And so the negative charge has some electric field that looks like this. And so at this point, we have some E minus that points like this. And so when we add the two of these together, it's like taking this vector and shifting it so the tail starts at the head at this one. And so this goes like this. The y components cancel, and then this is the vector E plus, this is a vector E plus plus E minus, which is what we're looking for. Okay? Good. So now what we're going to do is we're going to move into some calculations with electric field. And these follow in a very similar way to the calculations that we did with the force. So to remind you, when we wanted to find the force between two charged particles, the way we did that was to apply what's called Coulomb's law. And so Coulomb's law says the force between charge 1 and 2 is going to be equal to K Q1 Q2 over R squared. Now, if we wanted to talk about the electric field that one of these charges individually creates, that's to say that the electric field E vector is equal to K Q divided by R squared. And actually these aren't vectors for the form that I've written it in right here. Okay? So we basically want to do what we did earlier in the week and last week when we were calculating the force on a charge due to another charge. Only now what we're doing is we're saying, okay, well this positive charge here, let's say, creates an electric field. We want to find the electric field there. And we can apply the superposition principle to find what the total electric field is. Okay? So go ahead and take a little bit of time to do that one. Okay, so let's go ahead and talk about this one. So we have our point charges like this. So we have some plus charge, some minus charge. I'm going to give these some labels. So I'm going to call this charge 1. So this is Q1, Q2, Q3. And the magnitude of Q1 is equal to the magnitude of Q2. It's equal to the magnitude of Q3, which is equal to 2 times 10 to the negative 6 coulombs, right? That's just a given. And so what we want to do is we want to find what the electric field is at this point. Okay? So in order to do this, what we need to do, the vector electric field, E vector, total, is going to be equal to E vector 1 plus E vector 2 plus E vector 3. And so graphically what that looks like, I have some E vector 1 that points like this. So this is going to be, let me move this over here. Some E vector 1 that points like this. E vector 1, because that's the electric field from this one pointing here. We have some E vector 2 that's going to point up because this is a negative charge. So this is E vector 2. And then the last one, E vector 3, is going to point like this. E vector 3. And so what we need to do is we need to calculate each one of these independently and then add them together in accordance with the superposition principle. So the first one that we can calculate, let's start with the electric field that Q2 acts on this point. And so that's to say that E2 is going to be equal to K Q2 over R squared. And then this is going to be equal to 9 times 10 to the 9 newtons per Coulomb squared, times the charge, which is going to be the 2 times 10 to negative 6 coulombs, divided by the distance from here to here, which was a given. This was 0.4 meters and 0.4 meters. So this is going to be this 0.4 meters squared. And when you do this calculation, you end up finding that this one was 1.1 times 10 to the 7 newtons per Coulomb. Now, this value actually happens to be the same value that you have when you do the calculation for the electric field from Q3, right? Why is that the case? Why is it that the electric field as a magnitude from Q2 is the same as the electric field from Q1, or sorry, Q3? They have the same distance and they have the same charge, right? So this value and this value are the same. This is just some constant. And so this is actually also equal to E3, okay? Now the last one we need to do is just going to be E1. And so E1 is going to be equal to, again, KQ2 divided by R squared. This is a different R, right? Because now this R that I have here is this distance R here. And so in order to find this distance r, we need to use the Pythagorean Theorem, knowing that this is some side 0.04, this is some side 0.04. And so this says that this is 9 times 10 to the 9 newtons per Coulomb squared times 2 times 10 to the negative 6 coulombs divided by 0.04 meters squared plus 0.04 meters squared. And this is going to give me a value of 5.0, is that a 0? Is that a 6? That's 6. 5.06 times 10 to the negative 6 newtons per Coulomb. Okay. So now that we have the magnitudes of these, we need to break them into vectors in order to add them. So the first thing that we can do is we can say that E1 is going to be, it's going to be some amount in the x direction, some amount in the y direction. Remember, this was what E1 looks like. E1 looks like this, and so it has some part E1 in the y direction and some part E1 in the x direction. And this is going to be some angle of, let's do this one here. This is going to be some angle of 45 degrees because the square, it's a square, and so all of the sides are the same. And so what that says then, when I break this into components, this is going to be the E1 that I calculated here times the cosine of 45 times I hat plus E1 times sine of 45 times j hat. Okay. Now let's put in our E2. E2 is going to point up, and so this is going to be 0 in I plus E2 in j, and E3 is going to be only in the x direction, and so this is going to be E3 as a magnitude I plus 0j, okay? Now to find what the total electric field is here, we add these together, and then we'll see what we're going to get. Is everybody happy with this so far? Some people look a little unhappy. Maybe you should be unhappy. I think you should be unhappy, actually. There's something wrong here. Yeah.
Why is E1 5.6 times 10 to the negative 6? I got 5.6 times 10 to the 6.
Right, it should be to the 6, yeah. So that's one thing, so orders of magnitude matter. But there's actually something else wrong here, yeah.
Shouldn't, for E1, Sine part be negative?
Yes, yeah, so this should be negative. And the reason this should be negative is because when we look at our coordinate system, this is going down this way, right? And so because this is pointing down like this is the negative y direction, okay? So now everything looks okay, and the other one was correct in the first place. And so when we add these together, what we end up seeing is that in the x direction, this is going to be 1.5 times 10 to the 7 newtons per Coulomb in the I direction, plus this one was 7.6 times 10 to the 7 newtons per Coulomb in the j direction. Okay? That's it. Okay. Any questions about this? It's a very standard problem. You know, there's some things that we might change a little bit, but more or less, you know, if I'm going to ask you a question on the exam about electric fields and finding what the electric field for point charges is, it follows exactly this process. You have to find what the magnitude of the electric field is from each charge, and then find the components and the directions. Yeah?
Wouldn't the j hat be to the 6th?
J hat to the 6th. Where?
You got 7.
Oh, right, yeah, this is this.
Yeah.
This is the 6th. Yep, good. I was testing you guys. All right, other questions? Okay, so now, and you guys know I'm a fan of doing these things algebraically because I think it helps you think about the relationships between these quantities more than just the values. And so now what we want to do is we want to treat this in kind of an arbitrary way and say that now we have some charge of just Q for each one of these. And I've changed something else here, and instead of telling you that this is a square, this is going to be some rectangle that has some height of h and some width of w. So go ahead and spend some time on this one. I think now that you've done this problem and you've seen all the pieces, this one's going to be pretty straightforward. But the thing that's going to be a little bit different is how I'm going to evaluate cosine and sine. Make sure that you're drawing triangles to determine the relationships between these sides. Okay? Okay, so let's go ahead and talk about this one and then we'll move on to the next one. So in this one, we've kind of abstracted this a little bit by saying that we don't know exactly what the distances are, but they're defined by some distance h for the height and some distance w for the width. And we also say that these just have some arbitrary charge, and they're all the same arbitrary charge, they're just some charge q. Okay? And what we want to do again is to find what the electric field is at this point. Now it happens to be that because I kept this to be positive, positive, negative, the direction of the electric fields are going to be the same, it's just going to be the magnitude that might be a little bit different. And so in order to calculate what the magnitude of these are, we can plug in for this one, we want to find E2. So let's, let me give these labels. So this was 1, 2, and 3. So E2 is going to be equal to KQ divided by the distance from charge 2 to this point. This is going to be divided by h squared. Okay. E3 is, in this case, actually not the same as E2 anymore because the distances here aren't the same. But we know that the distance from Q3 to the point we're finding the electric field is going to be W, and so this says that E3 is going to be equal to KQ divided by W squared. Okay. Now, the last one that we need to find is the electric field from E1 acting here. And so in order to do that, we need to find what the hypotenuse of this triangle is, right? Because we have this side and this side, and so we can use the Pythagorean theorem to find that. And this just says that this is going to be equal to the square root of h squared plus w squared. Okay. So now we can take that and we can plug it in here. This is going to be KQ divided by h squared plus w squared, okay? And now that we have the magnitude of these electric fields, we can write them in component form. And that's to say that E1 is going to be equal to the magnitude of E1. And if I draw a triangle here to represent the angle here, so this is E1, this is E1y, this is E1x, this is the angle theta, then this is going to be the magnitude of E1 times cosine of theta, I hat, minus the magnitude of E1 times sine of theta times j hat. E2 is only going to point in the positive y direction, and so this is going to be 0 I hat plus magnitude E2 times j hat. E3 only points in the positive x direction, so this is going to be equal to the magnitude of E2 times I hat plus 0 times j hat. Okay? And we're almost there, but we realize that we've introduced something here that we don't know. And so we need to establish what theta is, or establish what cosine of theta and sine of theta are. And so in order to do that, we can go back to our distance triangle that we had here. So this was the width of W, height of H, and we can find what the cosine and sine of the angle are, knowing these three sides. Okay? So by definition, the cosine of theta is going to be equal to the opposite, or sorry, the adjacent, which is in this case W, divided by the hypotenuse, which is the square root of h squared plus w squared. And the sine of theta is going to be the opposite, which is h, divided by the hypotenuse, which is the square root of h squared plus w squared, okay? And then we could plug everything in and then add it together if we wanted to write the final answer in terms of all of the knowns that we have, but everything's parameterized here at this point, okay? Any questions about this one? More or less follows exactly the same as the last one. Okay, so now move on to something completely different. Here we're told that we have plates of a capacitor, and what a capacitor is, it's two parallel plates that can hold charge. And if you're holding charge on these two plates, what ends up happening is there's going to be an electric field between the plates. And so what we'd like to do here is to apply some of the things that we learned about kinematics from last semester in order to find, if I put some charge, let's see if this is a positive charge or a negative charge. A positive charge is placed by the positive plate. So we have, here's a positive plate. And remember, the plates of a capacitor are charged, or they can be charged, and if they're charged, they produce an electric field that points from the positive plate to the negative plate. And so what we want to find is, if I put this charge here, I have some positive charge right next to the positive plate, we want to find how long it takes to go between the plates if we know that this has a distance of 2 centimeters separation. So this is going to be 2 centimeters. And we want to find how long that takes and how fast it's going when it gets all the way over here. Okay, if we release this from rest. Okay, and we give you some additional equations that you'll need here, and these are just our kinematic equations from last semester. But something else to remind you is that the force acting on a charged particle as a vector is going to be equal to the charge of that particle times the electric field. Okay. So go ahead and spend some time working on this, and then we'll talk about it. We're going to come back to this question to actually solve it once I introduce the concept. But there's a very particular reason why we can't do what we did the last time. So last time what we said was that the force was equal to the charge times the electric field, and the force was equal to the mass times acceleration. And then we could use this in conjunction with our kinematic equations to say that the position as a function of time was equal to the initial position plus the initial velocity times time plus 1/2 at squared. And the velocity as a function of time was equal to, this was v0 plus at, okay? So we can connect these two together. So we can say that the electric field, or sorry, the acceleration A is equal to the charge times the electric field divided by the mass. But this is where we're going to start running into problems here, because the electric field for a point charge varies as the distance, right? Because if I'm this distance, or I'm this distance, or I'm this distance, I have a different electric field. And so this electric field is really some function of the distance. It varies depending on how far I've gone, which means that the acceleration varies with distance. And in order to apply these kinematic equations, we actually need to have a constant acceleration. This works for when you're close to the Earth and you say that the acceleration due to gravity is 9.81 meters per second. But even there, that's why you have to be very careful, because the acceleration due to gravity from the Earth is not 9.8 meters per second. It's 9.8 meters per second when you're close to the surface. But if you're out at the distance to the moon, you're going to have a smaller acceleration. So even that's just an approximation that we're using to be able to use this equation. But in this case, it definitely doesn't hold. Okay. So what might we do instead? What might we use instead? I think you were on the right track. Yeah, use work. So when we talk about work, we say that the work, by definition, is, so if we say that the work from an individual force, this is going to be equal to that force times the distance times the cosine of the angle between them. What did we relate to work to? Or if we said that we had the total work, this was equal to the change in something. The change in, the negative change in potential energy if we had just a single force acting on this, and that was there. But this is really the change in kinetic energy, right? You have to be a little bit careful to build this up. If I say the total work, I need the sum of all potential energy, but it is just the change in the kinetic energy. So this tells us really that what we want to apply here to find this one is conservation of energy. Okay. And so now that we've had this kind of segue into conservation of energy, I want to kind of lay out the equations that we've had so far and then put them in this table to organize them. So draw this table like this and put in the top left corner, this is Coulomb's law. So these are our vector equations. And then we also have our scalar equations. So the top left we have the force, right here we have the electric field. This is going to be the potential energy. And the electric potential ultimately. I'm not even going to tell you what that is. We're going to kind of point to that later. So we know the force between two charged particles from Coulomb's law. The force, and this is a vector, is going to be equal to K Q1 Q2 over R squared. I'm going to leave it as not a vector, but we know that it's a vector. We know it points somewhere. And then we also have the electric field. The electric field is going to be equal to KQ divided by R squared as a magnitude. We also know the connection between the force and the electric field now. This just says field. This says that the force is equal to the charge times the electric field. Okay. Now, going back to things that we learned last semester, we know there's some relationship between the potential energy and the force. And this is to say that the potential energy is going to be related to the force according to the force is going to be equal to, in some x direction, is going to be equal to the negative change in potential energy divided by the change in x. Okay? And this is itself an approximation. You really need to, if you know calculus, you need to use derivatives in order to show the next step that I'm going to write. But if I want to write what the potential energy is between two charges, what that says is that U is going to be equal to K Q1 Q2 divided by R. And this is the potential energy between charge 1 and charge 2. Okay. Now that I've laid out this table here, it kind of seems lonely over here, this empty box. And it seems like this one should point over here and this one should point over here as well. Well, there actually is another quantity that we're going to talk about more next class once we move past potential energy. And this is what's called the electric potential. And there's a lot of good labs that you're going to have coming up that are going to involve thinking about the electric potential in a conceptual way. But the electric potential is related to the electric field in a very similar way that the potential energy is related to the force. And so this is to say that the electric field in some x direction is going to be equal to the negative change in electric potential divided by a change in distance. We call the potential energy U, we call the electric potential V. These are connected the same way that these ones are connected, to say that U is equal to Q times V. And so from this one right here, we can see that to find the electric potential, we're just pulling off a charge from our potential energy. And so this is going to be K Q divided by R. Okay, we'll get more into this one next class. We have another calculation now with the potential energy. Or actually, I don't remember what order I put this in. I think I laid this out and then we came back to this one. Okay, yeah, so now that we know that we can use energy conservation for this problem, go ahead and spend some time trying to solve this one. But let's go ahead and solve this one. So, like I said, what we want to do here, because the force varies over the distance, we can't use our kinematic equation, so we have to use conservation of energy here. And to remind you what conservation of energy actually says is that if I have two states, call them state 1 and state 2, the energy in state 1 is equal to the energy in state 2. So E1 is equal to E2. And be careful when I'm using E here, I don't mean electric field, I mean energy. So E1 is equal to E2. And we can break the energy up in each state into two separate pieces. So we can say the energy in that state is going to be one part the kinetic energy, which is related to the motion of the objects, and one part potential energy, the tendency or the ability for an object to move. And so what we can say is K1 plus U1 is equal to K2 plus U2. And we know that the kinetic energy in general is going to be equal to 1/2 mv squared. And we also know that the potential energy between two charges is given like this. I laid this out before. So this is the potential energy between two charges. And so what that says then is if I have this setup here where this is 3 centimeters and this is 6 centimeters, let me call this R1, let me call this R2. We can write this conservation of energy equation like this because first we can say that the kinetic energy initial is 0. It starts from rest. And so we have K Q1 Q2 divided by R1 is going to be equal to 1/2 mv squared plus K Q1 Q2 divided by R2. Let's move things around to solve for V. So I'm going to subtract this term from both sides. I'm also going to factor it because I have this K Q1 Q2 common to both. So this is going to be K Q1 Q2 times 1 over R1 minus 1 over R2 is equal to 1/2 mv squared. I can multiply both sides by 2 over m to move this to that side, and then take a square root. So take a square root, this is what V is equal to, and when we plug the numbers into this, we end up finding that I don't have that written on this slide. So I actually don't know what the answer is offhand, but you can plug in the numbers that we had here, and then we would find from that what the velocity was. Okay, so that's going to be it for today. I'll post the homework hopefully today. It'll be due on Tuesday, and I'll also post the video, and I have the video from lecture, as well as I have a video that kind of goes through this this table that I made here.